Hey guys, so in today's lecture, we are going to study the last chapter of this subject, that is MHD, that is Magneto Hydrodynamic Power Plants. So we will call it in short as MHD. So the MHD power generation, the heat energy. So here the heat energy is directly converted into electrical energy without any without a conventional electric generator. So here we are not using the conventional electric generator. So the MHD power generator is a device which converts the kinetic energy of the electrically conducting material flowing in the presence of magnetic field directly into the electrical energy. So with the help of this concept, we will we can generate the electricity. So in conventional steam power plant, the heat is released by the fuel and is converted into mechanical energy. So by means of a thermocycle, and mechanical energy is then used to derive the electrical generator. So thus two stages of energy conversions are involved. So so that is first heat energy to mechanical energy, and then mechanical energy to electrical energy. So there are two stages, 1 and 2. So so uh, so the two stages are involved for energy conversion. So heat energy to mechanical energy, and mechanical energy to electrical energy. So therefore it has very low efficiency. So also the rotating machines has its associated losses and maintenance problems. So in MHD generation, the electric energy is directly generated from the hot combustion gases produced by combustion of fuel without moving parts. So the MHD generator is a heat engine operating on a turbine cycle and transforming the internal energy of gas directly into the electrical energy. So MHD is one of such method which has undergone considerable development, and this method can make use of temperatures of order 2300 degrees Celsius to 2700 degrees Celsius as compared to the conventional steam power plants, which can use maximum temperature range of so conventional uses maximum range of 750 degrees Celsius to 800 degrees Celsius only. So thus MHD generators are said to have high efficiency, high efficiency and low pollution. So this is the main introduction to MHD. So we'll discuss the principle in detail. So principle of MHD. So this is very much important, and it is asked many times in exam. So the principle of MHD is same as the principle of conventional electrical generator. So that is Faraday's law. So what is Faraday's law? So Faraday's law. So when an electric conductor moves across a magnetic field, when an electric conductor moves across a magnetic field, a voltage is induced in it which produces electric current. So voltage is induced and which will produce an electric current. So it is the same it is the same concept of the conventional electric generator. So in conventional electric generator, the conductor consists of copper strips. In MHD generator, solid conductors are replaced by gaseous conductors. So solid conductors are replaced by gaseous conductors. So this is conventional and this is MHD. So in so this is replaced by gaseous conductor. So what is this conductor? It is an ionized gas. So ionized gas. So it is an ionized gas if such gas is passed at a high velocity through a powerful magnetic field. So if it is passed through a high velocity through a powerful magnetic field, a current is generated and can be extracted by placing electrodes in a suitable position in stream. So let me draw it. So suppose so suppose as you can see that I have drawn uh, a diagram. So this is suppose a sketch diagram. So suppose from here the gas is moving in. So suppose gas is moving in, and from here suppose gas is moving out. Gas out. So and magnetic field is applied in the perpendicular direction. So magnetic field, and suppose the electrodes. So if the electrodes are at in the third direction, and if if the current, if it is connected, if it is these electrodes, by placing these electrodes are connected to a stream, so this will generate an electricity. So so this so this is voltage V, this is resistance R, and this is current I. So here as you can see, if this gas is passed at a high velocity through a powerful magnetic field, so current is generated and can be extracted. So this current is extracted by placing the electrodes in suitable position, that is perpendicular to the magnetic field and the gas stream, and this arrangement is this shown. This will provide a power directly. So if I have to draw a axis diagram, so suppose this is x axis, this is y axis, and this is z axis. Then so suppose electric field in is generated in z axis. So suppose gas is moving in x axis and magnetic field is in y axis. So this is the angle, is all three are perpendicular to each other. So an electric conductor moving through an magnetic field experiences a retarding force as well as an induced electric field and current, and this effect is a result of Faraday's law of electromagnetic induction, and the induced EMF is given by, that is E induced, will be given by U into B. So what is U? U is the velocity of the conductor and B is the magnetic field intensity, and the induced current density. So the induced current density, that is J, is given as sigma into E induced, electric current induced. So where sigma is the electric conductivity in mho per meter. So the retarding force on the conductor is the Lorentz force, and that is given by, so the Lorentz force is given by force induced is equal to J induced into B. So G induced into B is the induced current density into magnetic field intensity. So from an energy point of view, the moment, so from energy point of view, the moment of force through a displacement is converted into electrical energy. So that is moment of force is converted into electrical energy. Electrical worlds work by means of electromagnetic induction principle, and a direct conversion of kinetic energy into electrical energy by flow of electrically conducting fluid, usually gas or gas liquid combination, through a stationary magnetic field. If the flow direction is at right angles to the magnetic field direction, and an EMF is induced in the direction of the right angles to both flow and field directions, and this is a work energy conversion and is not limited by the Carnot principle, of course. So it is not limited by the Carnot principle. So it is work energy conversion, and electromagnetic induction forms the basis of operation for conventional electrical generators. So this is the principle of MHD. So this is very much important and has been asked in exams various times. So now we'll see another topic, that is power output of MHD generator. So what will be the power output of MHD generator? So suppose let's draw the MHD generator. So let's draw the diagram again. So suppose, so these are two electrodes. So electrode 1 and electrode 2. So suppose this is plus and this is minus, and if we are connecting an electrical circuit and giving a resistance R, so suppose this is the resistance R and voltage V. So this is suppose A, this is B, and suppose this is the distance D. Suppose it is having a distance D, and suppose the gas is moving at a velocity u. So as you can see in this diagram, the electrodes is having an area A, and it is held at a distance d along the axis z axis perpendicular to uh, both u and b. So this is the direction of b, this is the direction of b, and this is the direction of u. This is perpendicular to both u and b. So the magnitude of the force acting on a charge particle having charge q is given by, so the magnitude of force will be q u b, and this force, as per right hand rule, will be acting in the upward direction on a positively charged particle, and a positively charged particle will be collected by the upper electrode. It will be collected by the upper electrode, and negative charged particles will be particles by the lower electrodes, and causing a potential difference across them, and the resulting electrical fields between the plates is given by, so E will be equal to minus V by D. So D is the distance between the electrodes. So due to this field, the another force, that is QE. So QE will be acting on the charged particle in the downward direction, and the net force on the charged particle will be, so what will be the net force? So F net will be equal to minus Q V by D plus Q U B. So this E, this E I have used here, so we'll get QVD, and this force is also acting, so this I have added. So if no load is connected across the electrode, that is in open circuit condition, no current will flow and there will be no movement of the particles carriers between the electrodes. Therefore, no net force will be acting on the charged particle, and a voltage E0, open circuit voltage, appears across the electrodes. Thus, F net will be 0. So if F net will be 0, then QVD will be equal to QUB. So which is so V by D, uh, so which is QQ cancel, so voltage V will be equal to BUD. So that voltage, that open circuit voltage will denote as E0, will be equal to BUD, that is BUD. So this is the open circuit voltage, that is BUD. So internal resistance of the MHD generator is the resistance of the conducting fluid flowing between the electrodes, and thus it will be given as Rg will be equal to D upon sigma A. So now if an external load, that is RL, is connected across the terminals, so current starts flowing through the load, transferring power to the electrical load. So as maximum power transfer theorem, the maximum output, that is P max, is obtained when the load resistance is equal to the internal resistance, that is Rg. So when RL will be equal to Rg, so the P max will occur. So P max will be equal to E0 I. So that is open circuit voltage, that is V cross I. So we'll get the maximum power. So as we know that E0 is I into Rg into I, so that is I square Rg. So we can write that instead of I, we can write that is E0 upon, so E0 upon RL, the resistance RL plus Rg, E0 upon RL plus Rg whole square into Rg. So if we open the bracket, we'll get E0 square upon so here as we know that RL is equal to Rg, so we can write it here as 2 times 2 times Rg, so it's square, it will become 4 times Rg square. So but here is also so Rg square and here is Rg, so Rg and square will get cancelled, so we are left with E0 is E0 square 4 by 4 Rg. So let's put the value of E0, that is BUD. So it will be B square U square D square upon 4 Rg. So substituting the value of Rg in this equation, so we'll get the value of P max. So P max is equal to, so the value of Rg we are giving, that is D by sigma A, so we'll get B square. So P max we will get as, let me write it again, that P max is equal to B square U square D square divided by 4D by sigma A. So this is this is the maximum power, that is maximum power output per unit of volume. So it is given by 1 by 4 B square U square D square sigma A. So let me give the power output per unit volume. So let's take a and D in the other side. So here d square cancel, so we are left with sigma u square b square upon 4. So this is power density. So power per unit volume is given by sigma u square b square upon 4. So this is the maximum power output per unit volume. So thank you very much. So in the next lecture we will see the thermal efficiency of the MHD.